move to the next contribution, and that's from Dr. Pance Naumov. He did his undergraduate, he did his PhD at Tokyo, then was a Radcliffe Fellow at Harvard, and then moved to basically Abu Dhabi, the UAE, and he is associated with NYU at Abu Dhabi and NYU in New York at Washington Square or near Washington Square, and he is also director of the Center of Smart Engineering Materials he's part of so now I mix up your centers because you're director of one center and not of the other. So I hope I didn't mess up with all the centers, but you can put me straight. And I will not take more time from your speaking time. And Pance is going to talk about smart organic crystalline materials.
Thank you so much.
And once again, apology for messing up your directorship.
Yeah, I wear quite a few caps, so thank you very much for that beautiful introduction. Well, thank you, Tony, for inviting me. It's a pleasure being here. I'm honored and privileged to be speaking in this symposium. I'm kind of humbled also to speak after some of the idols and people who have inspired me and I look up to, in my career. And also, I noticed that this session has a nice transition from molecules to colloids, and now I'm going to talk something about crystals. So you're very inclusive, but also on the side of diversity, I must admit that Advisory Board has done an excellent job in including scientists from different ages, gender-wise, and also from different locations. And I'm going to represent the local research here because I am the one who lives in Abu Dhabi, in the UAE. And I'm going to tell something about what research we do here in the UAE. So my lab in NYU Abu Dhabi does work on crystals. But before going there, I just want to tell you something about why NYU in UAE. What was the incentive? So about 10 years ago, our former president, John Sexton, realized that NYU has to become global, and they established what's called the Global Network University. So basically, we wanted to bring the university closer to the students. And we established this network university where we have portal campuses, one here in UAE and one in China, because obviously the first stops were the growing economies. And then we have about 11 study away sites around the world, and the idea is to bring the students between these campuses, expose them to different culture, and prepare them to become next world citizens. So I would like to show you what we do in Abu Dhabi. This is a unique concept here because it's the only university in the UAE that provides a liberal arts education with a strong research component. So that is not really common in this part of the world, and as you can see, it's a very, very special environment. Now, what are our contributions of my group? Well, there are quite a few. I joined in 2012, and we organized a lot of activities here. At some of the milestones, I would like to mention that we formed the UAE chapter of the American Chemical Society in the country. And this kind of connects the community here in the UAE and establishes a platform for collaboration, joint applications for funding, as well as also connecting with the ACS, the largest chemical society or scientific society in the world. Then we established or prepared, also we made, two material science conferences. One is 2016 and 2018. We planned a third one in 2020, but it didn't happen because of the pandemic. And I would like to invite all of you to visit us in fall this year for the third Middle Eastern Material Science Conference, which, similar to Tony's conference, became a flagship material science meeting for the region. And it connects basically the local research community with the international community and also with editors of various journals. Also, we established the Emirates Crystallographic Society, and since this year, we have the Center for Smart Engineering Materials. Also, I would like to invite you to come and see that. And as you can see from this plot, my group has been quite active and produces about 50% or about half of the high-impact factor publications in the country, which I think is quite a tremendous achievement for these 10 years that I've been here. So this is just a slide to impress you, obviously. But I just wanted to show you that the main research focal areas of my group are about solid state, especially mechanical effects in crystals, We work on bioluminescent, bio-inspired materials. We work similar to Ben on self-healing and shape memory effects I will talk about a little bit at the end. Responsive polymers and much more than what you can see here, but this is just like a selection of our research. And in our research, we are inspired by soft materials and especially by nature. So we try to learn from nature and we try to apply it in the future to soft robotics. One of the things that is really important here is obviously the mechanical properties. When you think about crystals that we work on, you think about their brittle entities. So they are very, they break easily, they are soft and so on. But if you think about the mechanical performance, actually, the organic crystals take a very special place because they overlap partially, at least in terms of the Young's modulus, both with natural materials as well as with the materials that are used in robotics. So we saw a window of opportunity here where we can actually use organic crystals for applications in soft robotics as well as in electronics and other applications, as I will try to show you later in my presentation. Why organic crystals? Well, you can ask the same question for any material. Why any material? Because of all these possibilities that they open for electronics as a transistors, detectors, actuators, and so on, all of these could be made possibly more efficient by using organic crystals because first of all they're ordered, so that implies faster transduction of energy in the system. They are anisotropic and by definition they are light. So they are composed of light atoms, which means that they have low density, so in principle you can replace everything that you have with metals with organic crystals, at least in principle. All right, so again, when you think about organic crystals, I guess you probably think about these static entities, they're brittle, like a diamond, like a rock. And I would just like to show you that this is not actually the case. There are increasing number of examples which show that crystals can be dynamic in nature, something that Ben brought in his lecture. Now this applies to single crystals as well. So they can do a lot of rotations, bending. They can be used as machines. They can crawl, they can move around, and all sorts of acrobatics. But as I mentioned before, there's a lot of important implications because they are lightweight, they're ordered, they're anisotropic, and you can control them by using different stimuli, as I will show you later in my talk. So instead of powder, we decided to work with crystals because of their long range order, anisotropy, and lack of defects to a certain extent, obviously. Now, important questions that we would like to answer here is obviously the question of control. If you want to have a smart material, there has to be a certain level of control. The performance is something that hasn't been established well, and this is one of our priority areas. We would like to understand what are the limits, especially the upper limits of performance, because this will define the materials for engineering applications. And last but not the least, we would like to be able to quantify their dynamics, because being ordered materials, dynamics obviously will matter. There are so many examples now reported that it's very difficult to count them, and I get a lot of papers to review and a lot of examples which show that now this has become a sort of an observation, but many researchers hesitate to go into quantification because that's really requires special abilities, I would say, that extend beyond chemistry and go more into the realm of engineering. And our purpose is exactly to be able to kind of systematically look at these materials and estimate and find out what are their limits and how far we can go with their applications. And so this all evolved very nicely into a new field that we call crystal adaptronics. So what this is about in engineering, when you have a regular normal system, responsive system, you have basically a sensor, you have control unit and an actuator. And all these are three separate units. But in a smart system, all of them are integrated in the same material. And so if you think about the crystals, they can actually sense the stimulus, they process this information internally in the structure, and finally they respond. So we have actually crystal is a machine, crystal is a smart system or smart structure, especially these dynamic crystals that I'm going to talk about later. And so our way to do this is to kind of put the crystals on the global material science map in the materials space. And so we did a search for the past 30 years of mechanical properties of organic crystals. This was 3 years of work that I did back in Radcliffe. And what we found is that they nicely stand between the soft materials, such as polymers, and hard materials, such as metals and metal alloys. As you can see, these are the typical mechanical properties in terms of the Young's modulus, between 1 and 25 gigapascal. And really that qualitative statement that these are materials that bridge the gap between soft and hard matter, you can really clearly see in this plot. This also sets some limits of the people who try to report mechanical properties without looking actually how realistic these properties are. But now we have that window where we can actually put the organic crystals. And if you further zoom into this region, you will see that indeed they're outstanding crystals which can compete with some much harder materials. And we found that there are two actually classes, specifically very hard organic crystals, which are perhaps most prospective for applications, and these are either crystals having a lot of hydrogen bonds surrounding a central core, or crystals having a hydrogen-assisted intermolecular hydrogen bond, charge-assisted hydrogen bonds between zwitterionic molecules. And so perhaps those are the first candidates that we can consider when we think about applications. And this plot here on the left shows that there is any correlation with the distance, so the intermolecular hydrogen bond distances. But if you go into comparing the hydrogen bond density, which is basically a number of hydrogen bonds per volume of the unit cell, then there is some kind of small correlation, or weak correlation, I would say. And also the same goes with the hydrogen bond density per molecule, where we have the same property but divided by the number of molecules. And so these are, I would say, the first insights of how we can actually design very hard organic crystals, and those will be the best candidates for applications. Now there are so many of them out there that basically we need to categorize them, and one way to do that is to categorize them based on the outcome. So we have some that simply deform and change their shape, and some others that disintegrate, so they blast and they explode. And so you can think about categorization based on this outcome or the effect of their integrity. But what's more important is to look at their dynamics. Dynamic crystals, contrary to other materials out there, span a wide range of time scales of the response. So you can see several orders of magnitude. So we have very slow materials, but we have extremely fast materials that actually exceed the response from some other soft materials out there. And I think this is perhaps the most important asset that we should take into consideration for future applications. Anisotropy is another important asset, and this is just a simple example of boronic acid structure, where when you affect the material on different phases, you get very different mechanical response. So if you push the crystal on one side, you have bending, on the other side you have twisting, and on the third phase you have breaking. And so this anisotropy is not only about the mechanical properties, but perhaps more important, if you look at electronic and other properties, all of them are anisotropic, and it's important in which direction on the crystal you actually look at. So we did a lot of research on plastically bendable crystals, and one example is shown here. So basically, this anisotropy come to full extent, I would say, where you look at the mechanical properties. In this particular case, if you affect the crystal on one side, you get sliding of these layers, and the crystal will bend plastically. But if you push it on the other side, because you want to break the pipe interactions, then of course it will break. And so you have incongruous response of the same material when you affect it on different phases. There is a lot of effort to understand how this happens and why this is the case. I would say that we are still at an early stage of that understanding, but there are a number of groups using computational methods, including machine learning, to try to understand on a larger number of examples, to try to understand and possibly predict the mechanical behavior. I would say that we are very far from understanding them. Other ways to look at this is, for example, to use methods such as synchrotron radiation, infrared microspectroscopy, and relate these to periodic density functional theory calculations to see what is happening at both intermolecular bonds, and then to try to correlate somehow with the structure. But this is not an easy exercise always, because it requires some special technical requirements. So we tried to somehow quantify the force that crystal can exert. The problem here is if you use a UV light, it interferes with the band gap of the detectors. And so in this particular case, we use micropillars made from PDMS, and we use crystals that is bent by UV light, and then we measure the deflection of the micropillar, and based on that, we can calculate the force exerted by the crystal. And then having that information at hand, we can put them on a global materials property space and see where they stand. So for example, here you can see that we have low power density, and the reason for that is because they are very small objects, but they have quite large work density, which is comparable to some other systems. And then, of course, within that group of materials, you can also see that there is a better performing and worse performing materials, and that also gives us an important tool, I would say, to quantify the performance of these materials. Some side results of our research is one of them is shown here, where we actually found out that if you bend a crystal, you decrease the melting point in the bent region. Now, melting point being one of the most fundamental physical properties, it's very difficult to control. But here, because of the increased amount of defects in the melting region, as you can see from the thermal images here, we actually decrease it for a significant amount. So you can use perhaps these for as one of the way to understand what happens when you grind crystals, when you mechanically affect them in a more, let's say, rigorous way. But then it's also very important to be able to understand the foundation, the basics about this decrease in the melting point. And so some of my colleagues in New York are actually trying to model these defects and how they evolved throughout the material. So there is also an interesting research developing around superelastic organic crystal. So probably you are familiar with the concept in other materials. So elastic, when you apply a stress to a crystal, we go through this linear regime of stress strain, where we can basically use to calculate the Young's modulus. But if this application of stress is coupled to a phase transition, the crystal will be able to sustain a much larger strain for the same amount of stress. So instead of, let's say, having 2%, we go to about 12% strain. And in case this is reversible, so the crystal reverses back to its original state, we have superelasticity. But in case you have to push it back to apply force in the other direction, that's ferroelastic crystal. And these phenomena are recently observed for the first time in organic crystals. And not only that they are kind of resembling the same phenomena observed in metals, but I think there's a more fundamental difference, because in this case we're dealing with intermolecular interactions as opposed to metals where we deal with metallic bonds. And so I think this is a really important area and provides a lot of field for additional research. Our particular interest in materials, especially crystals, is very fast phenomena. So about 10 years ago, we discovered that if you subject some crystals to heat, light, or even mechanical pressure, they can move. And then they do so from several millimeters up to several meters. It's very important to understand not only why this happens, and aside of the visual appeal, but it's important to understand the amount of energy, elastic energy, that is accumulated within the material, and it is released in form of kinetic energy, which makes these things to move. So after a lot of research, we concluded that these are actually based on martensitic transitions, are very fast, and as I mentioned before, actually cover many scales of many time scales. So I think there is, if you look at this from the perspective of energy transduction, this presents some of the fastest system for energy transduction from one kind. for example, heat or light into mechanical motion or mechanical work. Some other aspects of our research are also to be able to quantify these phenomena. And what we tried here is to measure the rate of the progression of this phase transition across the crystal and then compare this with the rate of expansion. As you can see from this plot on the top right, we basically are dealing with fastest phase transitions in molecular materials. And the reason for this is these are martensitic, so they're non-displacive. We have military kind of change where everything changes in the same time. And this provides us with the opportunity to use this potential, this energy, to actuate other materials or to, for example, consider interaction with cells, for example, in the future. This is something we also work on, or some other potential applications. Of course, in this case, we have to use a high-speed recording because these are very fast processes in order to be able to track how does the phase transition progress throughout the crystal. But we also found that the actual expansion of the material is one order slower than the actual phase progression front, the rate of the progression of the front. And the reason for this is some energy dissipated from the crystal, and there is some kind of resistance of the crystal from to this process. So there are so many examples now reported, and this kind of shows that we have examples which are above room temperature, but also we have below room temperature. And the main reason that we have more of these above room temperature is because many of them were discovered serendipitously, where people were looking at the melting point. So they try to measure the melting point of the compound, and then they see something happens, but they really cannot explain it, so they just report it as observation. But I would say that there are many more out there, and we'll expect to see more of these reported. So how do we quantify these materials or the force they can exert? Our way is to use a very sensitive force sensor that we attach to the crystal, and then we subject them to heating, and then we measure directly the force. And so based on this, we can calculate the volumetric power density. And you can see from this plot here that they can compete to some other famous or some more common materials such as moving coils, solenoids, and so on. And they come even closer to some MEMS devices. Unfortunately, many of them disintegrate throughout the process, so it's not very easy to directly transfer this into applications. But in some cases, we have examples that they really retain their integrity over repeated cycles of actuation, and these are actually the most important for future applications. In this particular case, we discovered a material which is now, the paper is under review, where we have a simple crystal, guanidinium nitrate, which shows about 50% of expansion when you heat it over phase transition around room temperature. And this is a record holder, I would say, in the crystal expansion in some material, which translates into a very high work efficiency for this material. And sometimes you can look at very simple compounds. Maybe some of you are familiar with this compound, which is hexamethylbenzene. It's a very old molecule. Catherine Lonsdale determined the structure in 1928 to show that the benzene ring is planar and all the bonds are the same. And this is an example of thermoelastic crystal. So it's not martensitic, but it expands significantly, and when it does that, it can perform work. And so we can quantify this by some direct measurements of the force and compare this with other materials. So now we have thermosilent, but also we have many thermoelastic elastic crystals. And what we can do with this, after measurement of force, we can compare the actuator stress and actuator strain. And in this particular case, you can see, for example, that this material has a performance which is close to nanomuscles, electrostatic actuators and voice calls, and it can compete with some MEMS devices. Also, one of our discoveries back in 2016, it was a really good year for us we actually found a shape memory effect in organic crystal. So what you see here in the movie is crystal which has been subjected to mechanical force, it deforms, and then after you hit it, it goes back to the straight shape or so. And then you can go back and forth, similar to what would you see with the shape memory alloy, but in this case, it's a simple organic crystal. So what is happening here? We had to resort to synchrotron radiation and X-ray at the diamond to actually determine the crystal structure of this material, and we find two different forms in the two different parts of the material. So basically we have some sort of a bilayer that can be switched back and forth, and this accounts for the shape memory effect. There are some other examples where we use co-crystals, either multi-component crystals, where we also can measure this force. And you can see here on the right side, this is the co-crystal between two compounds. And by direct measurement of the force, we can estimate or we can quantify the force, and then we can compare these to some other materials. So in this particular case, we find that if you compare this with other materials, the crystals have small stress and we have intermediate to high strains, but what is important is they are really, really light. So they have low density, and also what is important, they are homogeneous. They don't include different parts as the regular actuators. And this provides a much, much easier way for implementation of these materials into devices. Also, the other ways to characterize them is to look at the work capacity and the density. And by doing this, we found that organic crystals, at least in this case, they are better than electroactive polymers and even some MEMS devices. But importantly, they are much, much lighter than these devices. And I think this is the greatest asset. So what we can do with them? We made some simple devices to just showcase possible applications. In this particular case, we have a crystal which is coated with metal, so it can be used as electrical fuse. Once you heat the crystal by transducing electricity, the crystal will break, and then it will break the circuit, and then this breaks and this acts as a solid, all-solid fuse. A lot of research recently in several groups around the world revolves around using crystals as optical waveguides. And this can happen in two ways. So you can either have a passive waveguiding, where you transduce the light and you just receive it on the other side, the same spectrum, or you can have active waveguide, where you shine light and you receive the fluorescence. And there is a lot of variations on this theme. For example, you can bend the crystal and make some kind of deformed the optical waveguides. You can put crystals inside the crystals and make some sort of hybrid materials. And also you can use epitaxial growth to connect broken crystal, and so weld it if it was broken. Perhaps this is a very interesting laboratory exercise, but in principle shows that things that you cannot do with other soft materials can be done in principle by using crystals. And so another thing that you can do is to try to control the spatial output of the optical waveguide, and this can be done by using crystals which are responsive to ultraviolet light. So in this particular case, we have ultraviolet light to control the shape, and then we use normal light to transduce it through the crystal. So basically we can have both spatial and temporal control of the light output. Now the problem is, how do we scale this all down? And our way to do this, and we have the problem with manipulating crystals on a small scale, is to use AFM. So we use AFM tip to cut, to slice, to bend crystals, and to manipulate them in all ways. And then using this technique, I have other examples to show you, but this is just one typical example. We can assemble them in optical circuits on a micro scale and then use them as microscopic optical transducers. now, all of the information that we received over the internet comes not in the visible regime, as you know, but comes in the near infrared. So our most recent endeavor was to shift from the visible range to the telecommunication regime. And in this particular case, we have a very simple amino acid crystal, which happens to be also very hard with Young's modulus about 40 gigapascal. We transduce a near infrared light, and we can transfer information in the telecom regime. So we are kind of expanding now this region to try to chemically modify the crystal in a way to open up or close specifically part of the transmission window in order to be able to block some information or transduce some other information. This is another way, another example of crystals which are used as semiconductors. And this is also an active area of research where we have mechanically compliant crystals which can be bent in all ways. And in this particular case, this one can be used either as optical waveguide and in the same time as a backgate phototransistor. So we're trying now to improve the efficiency and see how we can go out by implementing phase transitions and other phenomena together and couple them with these kind of semiconducting properties. Now, again, back to 2016, I mentioned it was a good year. This was also the year when we found the self-healing phenomenon in crystals. This is where I would relate to Ben's lecture. Again, disulfide chemistry, we went through a library of dynamic covalent bonds, and disulfides appear to us as the best choice. It's a very simple compound, this pyrazyl diethyl thioram here. And what happens here is you break the crystal in two, and you put the pieces together and hold them for 24 hours, and the crystal heals itself. And it opposes gravity. You can poke it, and it doesn't really split. But if you want to get more quantitative way of looking at it, you can use a computed tomography to look throughout the crystal and then see what has happened inside, and we find that it has healed in its interior. Unfortunately, in this case, the self-healing was very small, about 7%, but now recently we have increased with this with a completely different chemistry, which is boronate chemistry, to 68%, so one order of magnitude in the healing in the first cycle, which drops back down to 44% in the fifth cycle. So we also tried now to other compounds, especially perovskites, and it's working very well in single crystalline state. Other things that you can do is change the stimulus. So I talked about light, I talked about heat. Recently we have been doing coating crystals with polymers that respond to humidity. And in this particular case, we have an example where crystal has been coated with humidity responsive polymer, and we see again deformation, and we have also a linear change or linear dependence on the level of the humidity, and that makes this crystal a kind of a humidity sensor. So not only humidity, we can use also other stimuli. So we can use magnetic fields. If you have a crystal which is coated with a polymer and we use magnetic nanoparticles on one side, this gives you the opportunity to control the bending or deformation in medium other than air, so in water, as it is shown here on the top right, but also to make some small soft robots where you can control basically the motion of the crystal along surfaces. So now we have accomplished spatial and temporal control of the deformation without these depending on the intrinsic property of the crystal. Now they depend only on how do we manipulate the magnet around the crystal. In another example, we use the temperature, and this is very, very fast transformation, as you can see. But also, you can also think about making these some small soft robots or grippers, where when they cool down, they curl, and they take objects, and they transfer the objects from one place to another. And also, we can think about optical thermal sensing applications. So all kind of research is going on. Again, in this case, we use the elasticity of the crystal, but we add a value with coupling this with polymers, which bear a range of functionalities. And this hybrid approach actually gives us a lot of opportunities to play with. So I would like here to summarize my talk and tell you that dynamic properties are important, not only for molecules and for other materials, other soft materials like colloids, but also for crystals. The biggest assets of crystals is their long-range order, and this gives us a chance to transfer energy much more rapidly and efficiently. The anisotropy in their structure is really important because this means we can control the properties, or we can elicit properties in different directions. So we would like to be able to set the crystals as a separate class of engineers, to set performance indices and bring these to the attention to the engineers, which will be using it for other applications. What we don't understand at the moment is the effect of intermolecular interactions. How can we control or play or use different types of predetermined intermolecular interactions, perhaps by using supramolecular chemistry or using the syntons to actually elicit specific response and not just get it by serendipity. I see the softness of the crystal not as a disadvantage, but as an asset, because the propensity of these intermolecular interactions to absorb the strain and to dissipate the strain actually makes them much more resilient to mechanical impact than some other systems out there. And finally, we need these, as chemists, always interested in structure property correlations, so I think this is an important aspect of this research. Finally, this is my research group of very diverse researchers and students coming from many countries, and I would also like to invite you to visit us in Abu Dhabi and also to follow us on social media. So thank you for your attention, and I'll be happy to answer any questions.
Thank you very much. This is a very interesting talk. Again, we have time for questions, and I will start by inviting the audience on the Zoom link to put in any questions that they may have. In the meantime, I look around the audience and
Very nice.
Oh, sorry.
It's a new area I'm not very familiar with it, so maybe my question might be more naive. Can you tell us a little bit about the crystal structures and whether in some of the transformation, do they go through displacive transformation, first order, second order? Can you give us some insight?
Yeah, this basically depends on the type of deformation that you're looking at. So we have elastic and plastic deformation. There's a lot of argument now how this happens, because we have some direct information only in some cases, especially the case of elastic crystals. And in this case, what we know is that we have separation on the one side of the crystal, and then we have shrinking on the other side of the crystal. In case of plastic deformation, it's more about defects. So we have evolution of defects and basically moving of these defects along the crystal. But in case of the martensitic transitions, basically this is the same method and the same principle as any kind of other martensitic transition. It just happens in organic crystals, and we have the intermolecular interactions to mediate between different molecules to kind of transduce that energy throughout the crystals. So it really does depend on which kind of phenomenon you're looking at.
okay. Sorry, Bettina. Yeah. Yes, sorry, the microphone there. Yes.
Thank you. Thanks a lot, Pancho. That was a wonderful talk, very exciting. So, I was wondering this sort of thermosalient or, this like behavior or transformation of energy, light energy or thermal energy into mechanical energy that is typically used using air as the environment, right? I mean, these jumping crystals, they jump around on the microscope, plate basically. Have you ever thought of using these thermosalient features to, for example, propel particles in solution? I mean, I guess that probably has been tried and done, but I was wondering, how does the medium affect these phase transitions and this energy conversion process?
Thank you for that question, Bettina. So basically, the medium plays an important role because what you have here is motion through the medium, and that depends on the drag forces from the medium. So if we exclude the air, for example, in work of vacuum, we remove the drag forces, which become increasingly important for smaller particles. Keep in mind, these are very small particles, right? So I would say that this is possible, but there will be some resistance, and in principle, you can accomplish either water or any kind of other medium that doesn't dissolve the crystal. So it is possible, I would say.
Tony? Yes, you need a mic. Okay, there it is.
Thank you. Thank you very much, Pance. That's a really nice talk. Have you done very much in the way of DFT calculations and lattice dynamics calculations and so on, to like calculating the compliance matrix or looking at your phase transitions with variable temperature calculations?
Yes, we are starting to look at this now in collaboration with somebody from Sorbonne and a couple of other people also from NYU and from Australia. And we are trying to understand and to model, first of all, the rate of the progression of the phase front. Our initial conclusions are that defects are really important. These transitions always start at one of the corner acting as a defect and progress very fast. But if you have a defect on the way, that really alleviates the rate, and it has a significant impact. It's not easy to model these, especially when it comes to completely different systems. Some of them, for example, are organic and some are organometallic, so we have issue with modeling organometallic, obviously. But we are working on that, and it's very, very interesting to be able to understand how that happens.
I'd kind of just make a comment as well.
Sure.
That on Thursday, His Highness and I and Mike Klein visited NYU Abu Dhabi, and we were super impressed by the nice facilities that you have there.
Thank you so much. Yeah,
really nice.
I wish I was there to host to host you. We look forward to welcoming you again.
Yeah, we were hosted by your
fall.
Vice Chancellor, so it was a kind of,
Thank you so much for that.
Yeah.
I quickly look around. If possible, I should like to ask one question just myself, and that refers to one point you raised at the very end, namely to be able to predict the properties. And these are fairly complex molecules, so you inevitably run into the polymorph problem. So
Yes.
what would you like to comment? I mean, of course, the polymorph problem has been compared to the protein folding problem, except that proteins have evolved to reach their native structures, whereas crystals have never evolved to get to their most stable structure. So I would like to know what you think about this.
It's $1 million question.
Thank you.
Many people around the world obviously are working on polymorph prediction, and these are by definition polymorph transition, at least some of them. So I think it was very difficult to predict polymorph transition, and especially polymorph transition which has this kind of properties. But what we can understand based on our cumulative data so far is that there are several conditions that the crystal structure has to have in order to be able to undergo such transition. And those are, the crystal has to be soft. So in most cases we have soft crystals because we need the crystal to be able to absorb that elastic energy that develops. Then we have also, crystal has to be devoid from three-dimensional strong intermolecular interactions. We see crystals which have very weak intermolecular interactions, like for example layer structure, and we see crystals which have a small core surrounded by non-hydrogen bonding groups, but we never see in a three-dimensional structure. So I think those are some of the properties that need to be fulfilled as a prerequisite for this to happen. Whether it will happen in every case, that's a separate question. I would say.
Well, thank you very much. I should also cut off my own question because it's time for the break. But first of all, I should like to thank you and all speakers in the session for their wonderful contributions.
Thank you.